Hello, Asymptotes, grade 12 matriculants. This is your chance officially now. Welcome to the show. My name is Abraham, and I'm with John. John, how are you?
Abraham, it's really nice to be with you and to be with you, grade 12s. Now, don't fall off your chair. This isn't
I'm shocked myself.
This isn't a science show, but our regular presenter for grade 12 maths got stuck in traffic, couldn't get here on time. So, you know what? The show must go on.
Of course,
and we've
learning
got
must still take
we've
place.
got to do the learning. So you've got me this evening. We're going to be doing something really exciting, and I hope you're ready for it. We're going to be looking at a section of work that carries quite a lot of marks in the grade 12 exam. So make sure you've got your pens and your papers, you download the notes, and you get into it, because we're going to be working through making sure that you understand all about functions and inverses.
Nice one. I'm really looking forward.
Okay, shall I go to the board?
Please go.
Okay, we'll do this.
Right. As John takes his place, Asymptotes, I have some good news. Are you one of the next future stars? Well, if you are, Future Stars inspires young people to believe in themselves and also the power that education has in helping them achieve their dreams. So if you're one of them who says that I am a future star, simply log on to sastudy.co.za and find out how you can enter and explain why are you a future star. And lastly, you can tell us how do you dream it, believe it, and do it as a mindsetter. Already so many other mindsetters have entered. Guys, let's support one another also and vote for one another. The competition is open only to South Africa and to mindsetters, or to everybody, young person that is between the ages of 16 and 21. There are so many great prizes to be won. But now, getting ready for the functions and inverses, chat with me over the Facebook page. We are on facebook.com/LearnExtra. You can also follow us on Twitter @LearnExtra. And lastly, download your notes for today's session on learnextra.co.za/live. John, take it away.
Abraham, thank you so much. Guys, let's get into it. Now, I know that if you were watching the grade 11 lesson, then you would have seen Dean has been doing a whole lot of revision that's really important for you guys to take note of as well, because functions builds up from grade 10 through to grade 11 and then into grade 12. Sometimes we do things a little bit differently, particularly with the new curriculum in grade 10 and 11, but you really do need to master this section. As I said in my introduction, this carries a huge amount of marks. If you go to any of the past previous exam papers, you will see that there are questions on functions and inverses that carry quite a number of marks. If you can be familiar with this, there are marks in the bag. Really important that you get this. It's part of paper 1, so make sure that you're sorted out. So let's start right from the beginning, because I know that you've heard a whole lot, but what is a function? Let's try and answer that question first of all and get to it. Now, in this lesson, what we're going to do is we're going to do the following. We're going to investigate. Notice the science word there, but we can do maths investigator as well. When the inverse of a function is a function and when it is a relation. Hold on. What are you saying to me? There are relations in maths? I thought I only had to deal with my mother-in-law. No. Guys, there are differences between functions and relations. We need to be very clear about that. A relation is a mathematical term, just like a function is a mathematical term. So we're going to define that. We're going to investigate what makes a function a function, and when are the inverses of a function as well, and when are the inverses of a function a relation. Added to that, we're going to ask ourselves, is it possible to change a function? Can we do something to change a function so that its inverse is a function? So we'll talk about that and we'll get into that. And in all of this, we're going to do a couple of exam type questions. So I thought what we would start with is just that basic question. What is a function? What are the types of functions? Let's do a quick brainstorm, a revision. How many functions can you name? Post them on the web page right now, the Facebook page. And Abram's going to give me a list of functions that we know that are really our functions. In the meantime, I'm going to do some mapping. I'm going to talk about this question. What is a function? So let's remember what a function is. It's a mathematical device where we can take a set of numbers or variables, and we sometimes call those input values. And we take these input values, which we sometimes give a value, a variable x, and we say this term function takes this, all those numbers that are input or x values, and it does something to it. It follows a rule. And after the rule, we get some things at the end. We get a set of numbers. These numbers are called the output values. Okay? And we give those output values a special symbol. Usually, we say those are the variables, those are represented by the variable y. So x's are my inputs and y's are my output. Now, guys, I know that's basic, but lots of people forget it. And we need to make very clear about the basics that we've got here. So, what do we recognize about this thing called the rule? The rule for a function means that for every input, there is a unique output. So for every one of these numbers here, there has to be a unique one. One of these has to go to only one of those. So there's a linking like that. We can't have one of these going, that one going to two of those. That can't be. That's not a function. So the yellow line represents a mapping which is one to many. Okay? One to many. It is not a function. A one to many is a relation. So let me write that down so you've got it clear. One to many is a relation. There are two common types of mappings for functions. The obvious one, which is the one that everyone will think about, is 1 to 1. For every input, there is exactly a unique output. We call that a function. But we could also have a scenario when we have many of these things going to 1. And that's also a function, because many of them, all the inputs just have one number as the output. Okay? So many to 1 is also an example of a function. There are lots of examples of these, and we need to make sure that we understand them. We can name them, we can identify them, we can look at them, and we can make sure we've got them. So, guys, when we say that's the idea of a function, that's the idea of a relation. The blue line represents the function, so that's a function. And the yellow line represents a relation, because it's one to many. Then what we need to recognize is the simple test. And I know that last week Liesel went over this with you, but if you draw a graph on any set of axes and you do the vertical line test, you will be able to determine, is something a function or is it a relation? Let's make sure that we've got this sorted. So if I take some examples, Abraham, I think it might just be time before I sketch these. Are guys putting things on the Facebook page? Give me some answers. What are the functions that they've given?
I have Mokosu has given us 6 of them.
Okay, give me one at least.
Exponential.
Okay, an exponential function. So typically, an exponential function would look like something like that. It would be of the form y equals a number. I'm just going to say 2x, 2 to the power of x. And we know that's going to go through the point 0 and 1. Okay, so is it a function? Let's check it. Let's check it. Let's do the vertical line test. Take a straight line. If I do that, vertical line, how many points does it go through? Through that pink line. How many times does it go through it? Abram, give me an idea. One or many?
Many. One.
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 It's going straight down
Yes.
through 1. Okay, let's move it along. If I put it over there, how many times does it go through the pink line?
Many.
The pink line, just that pink line. So where's the point of intersection? Have a look. It's dropping straight down and it's intersecting at that point. Do you agree? So it only passes through one point. Okay? And so that's why we can say the exponential function, is the graph y equals 2 to the power of x, is an exponential function. If we run that white line across there, hope you can see it's cutting at one point. For every x value, for every number of x, there is only one output. There is only one y. Do you get it?
Yes.
Okay,
Yes.
cool. So give me another function that we can look at.
Straight line.
A straight line. Excellent. So let's apply that. We're going to take a straight line. I'm going to put a yellow straight line. I'm just going to put it over there. And let's play with the straight line now. This particular straight line, have a look at it. We're going to have a look at and see what happens to it. If we run the white vertical line through it, can you see it's cutting in one point? Only one point of intersection. Okay? So that tells me that that vertical line, that yellow line, as I've drawn it now, is a function. It's a mapping 1 to 1. I hope you've got that. Let's change it around. What happens when we do a horizontal vertical line? The type of equation that we could have here is this could be y equals, well, a number. So y equals 5. Now, look over here. For every x value here, it doesn't matter what the x value is. Okay? There are many x values. What do they all give? It doesn't matter if I take f of minus 1, or I take f of minus 50, or if I take f of 50. What can you tell me? What's going to be the output? Doesn't matter what my input is. All of them are going to give me the same output. They're going to give me the same output of 5. So this is an example of many things mapping to 1. It's a many to 1 relationship. Is it a function? Well, you check. Look at the straight line again, the vertical line test, and we're going to pick up the white line, and we run it along here. Can you see? At every point, there is only one intersection. There's the intersection. It's only cutting the yellow line at one position. If I move it to that point there, only cuts the yellow line at one position. So it is definitely a function. So over here, it cuts the yellow line at one position. So guys, the straight line is a function if it's of this form. But Abram, you know what? There's a problem. Because there is one example of a straight line that is not a function. I'm going to ask the learners out there. Can you come up with an equation of a straight line that is not a function? How about that as a challenge question?
Nice challenge.
Okay, so guys, Abram's going to post that question on the Facebook page, and let's see if you can comment below the post. He's going to write it now. What is the equation, or give an equation of a straight line that is not a function? All of the others are functions, but there's a particular form of a straight line that is not a function. I want you to think about it. Make sure you've got this sorted so that you can identify. Okay, I want to talk to the learners out there. So what other examples of functions did they give us?
Quadratic.
A quadratic. Excellent. So I know my axes are getting a little bit messy. So you know what? I'm going to extend the page, and I'm going to go down to the bottom here, and I'm going to say, let's talk about quadratics. Now, there are two forms of quadratics, and what we can do is, first of all, let's do the one with a minimum value, okay? And let's ask ourselves the question, what about this one? If I move my vertical line through it, how many points is it cutting the pink line? How many points do you think, guys? I think it's only cutting at 1 for every individual x value, there is one y value. But take a look at something. We know that a quadratic equation is actually the graph of a parabola, but if I'm very careful, what I'd recognize is that it's not a unique answer. So this y value, this output, is the same for this x value for x equal to x1 and x2. They have the same y value. So this is a many. There are two inputs that give the same output. So 2, 1. Okay. I hope you've got that. You can recognize that a quadratic function is, a quadratic equation is a function. The parabola is an example of a function. Okay, now, you haven't mentioned it. There's a third one that I want to look at, and that's the hyperbola. But you know what? I think it's time for a break.
On that note, I'll also leave them with that challenging question. We'll take it after the break.
So, guys, don't go away. Don't go too far either. You've had enough through the afternoon. Get your thinking caps on. Post on the page. Abram?
Right. Mindset is, I'll be waiting on the page. See you after the break. Welcome back, matriculants. And as we've posted the challenging question on our Facebook page, John, I have some answers for you.
Excellent. Great, guys. Now, in case you have just joined us, it's not a mistake. You're not watching physical science. Yes, I do know a little bit of maths as well. I don't always present maths, like to keep in the background. But here's the challenge question for you. Which straight line is not a function? We've illustrated some that are functions, those that have a gradient, they are functions, and those that are parallel to the x-axis, they're functions. Which one isn't? What are the learners saying?
I have a majority saying x equal to a, and x equal to 2, x equal to 3, x equal to 4. And another one that says y equal to 4.
Okay, let's check this out. Now, guys, if that's my Cartesian plane, and that's my set of axes, when I say I want the line x equal 2, then it's a straight line down there where all the x values, these points here, will all have the x coordinate of 2. So it could be 2 and 1, 2 and 4, 2 and 6, all of them. And down at the bottom here, 2 and minus 1, and 2 and minus 4, etc. So what do you notice? There is one input and many outputs. Notice if we took the vertical straight line, that vertical line test, okay, and I took my vertical line and I moved it, and I'm going to say to myself now, how many places does this vertical line cut my yellow line? Now, forgive me for not drawing freehand straight, but all of those points would be on the same vertical line, okay? So they would cut in infinitely many places. This is an example of a one-to-many relation. It's not a function, it's a relation, because it's cutting in more for every input, for the unique input, the 2 value, there are many possible answers. We don't like that when we're dealing with functions. Okay. Now, thank you for participating. I hope this is helping you. We want to do a typical exam question just on functions generally, and then we'll pick up in our next section a little bit more about inverses, and we'll play around a little bit with inverses. So, the one that hasn't come up for a while, we've spoken about straight lines, we've spoken about quadratics, about exponentials. What about the hyperbola? Okay, let's do a question on the hyperbola. And here we go. Oh dear. What does it say? It says, consider the function, tells us that it's a function, and its f of x is equal to 3 divided by x minus 1 minus 2. Okay. The first thing that you need to know when you get this equation of a hyperbola in this form, then you need to start to recognize what's happened to it. Remember, the original basic hyperbola from grade 10 is going to be written in this form. Y is equal to k over x, where k is a number, and we could even call that an a plus q. If we make the q 0 and we make the k 1, then we would get something that looks like this. And I'm just quickly going to sketch it. Let's make the k be positive as well. Then we're going to get the graph looking like that and looking like that. If the k was negative, that's for k being greater than 0. If the k is negative, then it will be in quadrants 2 and 4. It will look like that. K less than 0. Okay, got it. So that's where we start with our parent function looking like that. Now we're going to do some shifts to it. We're going to change it, move it to the left, move it up and down, and we need to understand what's going to happen to this very important word. Whenever you get a hyperbola, they're going to ask you about asymptotes. Now, what is an asymptote? Guys, I want you to think about this. An asymptote is an amazing phenomenon in mathematics. Now, Abram, I don't know about you, but when you promised something and you work hard to getting it, it's a wonderful sense of actually achieving your goal. Don't you agree?
I do.
Whether that's, I want to run 800 meters in 2 minutes, or it's, I want to work so that I can be busy all the time, or I want to save up money so I can buy a new CD. Whatever goals you set,
Yes,
it's great to achieve them, isn't it?
that's true.
Okay, so can you imagine what it must be like if you set a goal and you get closer and closer to that goal, but you never get there? That must
Painful.
be
It's very
painful.
discouraging.
That
And
must-
it always happens generally in life.
Okay, so guys, the message here, a life message, is don't give up. Life isn't like this all the time. You can reach your goal. Don't think, I'm getting closer and closer to my goal, but I'm never going to get there. No, you can get there. You've got to push through. Okay? But in mathematics, this idea of an asymptote is an important one. You get closer and closer, but you never actually get there. Okay? Now, that's just the rough translation for it. In mathematical terms, what we need to recognize is that x can never be 0, okay? And y, in this basic form of the equation, can never be 0. Because we can't divide by x, and if we have q equals 0, and we just ignore that for the moment, then a number divided by a normal number, a number bigger than 0, cannot ever give you make y 0 by dividing. You can never get to 0. You could try getting bigger and bigger and bigger, but you'll never get to 0. Okay. You could try getting smaller and smaller, and that would get infinitely large. So make sure you understand what this word asymptote is. Now, having spoken about that, we need to look at the equation given. And we need to write down the equations of the asymptotes for f of x. Now, the first thing I'm going to say is, what value of x am I not allowed to use? Have a look at it very carefully. We've got f of x, and it's equal to 3 over x minus 1 minus 2. Now, immediately you should recognize this denominator, the bottom here, can never equal 0. So when would it equal 0? If x equals 1. Because 1 minus 1 would give you 0. Division by 0 is an unknown. It's not allowed. Okay? It provides the asymptote. So the first equation that we've got is x equal 1. That's an asymptote. Now, how else can we find the asymptote? We need to look at this very carefully. And we're going to say to ourselves, what will the y value be? If I want y to be 0, okay, I know that I can't make the y value to be 0, but if the y value was minus 2, then take a look at what's going to happen. Minus 2 equals 3 divided by x minus 1 minus 2. Now, minus 2, not minus 3. Don't get carried away now. So it's minus 2. If I add 2 to both sides, then I'm going to get the following. If I simplify this, I'm going to get 0 is equal to 3 over x minus 1. Is that possible? Can I take a number, any number, and get 0 from a fraction? Can't do it. So if y equals minus 2, you should be able to remember this, that this term gives you your asymptote. So when y is equal to minus 2, and I've just expanded on that so you can see it. So the two asymptotes, x equal 1 and y equal minus 2. Hope you've got that. Now let's move on to the next question. We're going to need to use this because I can see we're going to need to sketch the graph. Look over there. So the next part, calculate the intercepts of the x and y axis. We want to find the intercepts. Where does this graph cut the x and y axis? Remember, the original parent graph, the asymptotes of the original one, the parent function over here, the line y equals the line y equals 0 and the line x equals 0 were the asymptotes. This graph has moved. Our graph has moved. The asymptotes have moved. So although the original graph can't cut the x and y axis, the moved graph, the transformed graph, the translated graph, it can cut the x and y axis and it can have an intercept. We've got to find them. Now remember, how do we find the intercepts? We're going to say, first of all, let x equal 0. So where's our graph? We're going to take the value down, and we're going to say it was f of x equals 3 over x minus 1. So we're going to say y equals 3 over x minus 1 minus 2. Just check it, minus 2. And there we go. Now, let x equal 0. We're going to say, what's y going to be then? We're going to say 3, 0, minus 1, minus 2. Now, I hope you can see that that gives you a value of y equal to 3 minus 1, which is going to give you negative 3. And then you're going to subtract 2 from that, and that's going to give you a value equal to minus 3 minus 2 minus 5. Hope you've got that. Quite a relief when you get this out. What does that line look like? Y equals minus 5. It's going to be a parallel line down at the bottom, y equals minus 5. That's the value of the y value. So the intercept, we need to, it's not a straight line, it's a point. We're going to say where x equals 0, y equals minus 5. That's where the line will cut. So let's do the next one. Let's make, I'm going to change color, so we've got it. Let's make y equals 0. And we're going to say if y equals 0, let's take into that function, 0 is equal to 3 x minus 1 minus 2. Now, take the minus to add 2 to both sides, and we'll get 2 is equal to 3 over x minus 1. And multiply both sides by x minus 1, and we will therefore be able to say 2 times x minus 1. I like to put in all the steps so I don't make a mistake, because I'm just being a little cautious. So 2x minus 2 equals 3. And if I now add 2 to both sides, I'm going to get 2x is equal to 5. So x is equal to 5 over 2, which I can write as 2.5. Notice the sign is positive, so the point that I'm looking for is where the value is 2.5 and the y value there is 0. Okay, so I've now got my intercepts, I've got my asymptotes. It's time for me to sketch the graph. So let's have a look at what it looks like and quickly just do the sketch and then we can move on. So there we go. Write in the y, write in the x, put the arrows on. If you're asked to sketch, don't just be slapdash. Make sure that you sketch as well as you can and extend the line down a little bit because I'm going to need to do that. Right, so where are we? What's the first thing I'm going to do? The first thing that I'm going to do is I'm going to try and find this line. X equals 1. It's an asymptote, guys. I need to represent an asymptote as a vertical line, a straight line. This one passes through the point x equals 1, so it's going to be vertical, passing through that point, and I'm going to draw it as a dotted line. So let me pull that out, and let's get my dotted line. And over here, I don't have a dotted line. I'm going to change this one to dotted in a second. So just bear with me. Draw that in, and I want to make it dotted. And I'm just going to change it very quickly to a dotted line. And there's my line style. Change it, and there we've got it. So here I have a dotted line. That represents the asymptote x equal 1. Where's my other asymptote? Where's my other asymptote? Y equals minus 2. So let's pick this line, and let's take this one, and let's copy it, and we're going to switch it around. And quickly put that in, paste it, and there we go. We want y equal minus 2. Straight line at the bottom there, I filled it in. Y equals minus 2. Now you'll see my lines don't look terribly straight anymore, but we were just asked to sketch, so I'm not going to fuss too much. This line is equal to y is equal to minus 2. Got it? I hope you have, and I hope you're following, because we need to now draw in the different parts of this graph. And how are we going to do that? We're going to look at the intercepts, at those two intercepts. 0 minus 5, so 0 minus 5, so I've got to go down a little bit more. So let me extend my x-axis. It's just drawing freehand here, so let's draw it a little bit further. If that was minus 2, let's say that's minus 5. So this is going to be the point 0 minus 5. Okay, just want to change that so it doesn't look like a 6. 0 minus 5, and that's one point. The other point was the point 2.5, 0. See it? 2.5, 0. So over here is the point 2.5, 2, 5, and 0. So what's my graph going to look like? Well, looking at the function, you will see that it has a positive number in front. So because it's positive, there's no negatives there, we recognize it's going to be like one of these ones here. It's going to be in the first and the third quadrant. So I'm going to draw my lines in the first and the first and third quadrant, and it must look like a hyperbola. So it's going to go down like that, passing through that intercept, and on this side, it's going to pass through that intercept like that, carrying on straight downwards. Okay, now I know I've drawn it rather big, but I hope you can see the method. Guys, you might not get this particular hyperbola in your exam, but I hope by following my instructions, you've been able to see how to draw these. Practice them, practice them, practice them, so that you're very familiar. Okay, Abram?
All right, to the break, we're going with the words from Sovu saying, you know what, Abraham, the show is so enjoyable because a science teacher is in the building and he rocks still. See you after the break. Welcome back, matriculants. Still learning more, I can tell, because Maputa says, thanks a lot. I'm enjoying the show. The lesson is very, very much insightful, and John is just too awesome. Guys, let's learn more. Get on the page, and also if you have some questions, I'll be there to assist you and other mindsetters, and let's help one another. Our Facebook page is facebook.com/learn extra, and let's learn more. John, take it away.
Abram, thank you. Now, guys, we've just warmed up, and I can't believe we've only got about 18 minutes or so left of this lesson. The key thing that we wanted to ask right in the beginning, we've understood what a function is, but what we want to investigate is it possible to know when the inverse of a function is a function and when the inverse of a function is a relation? And can we do something about these things that end up relations to make them into functions? Well, we just want to get right into that. Remember what we've said right in the beginning. We said that for something to be a function, it must be a one-to-one mapping or a one-to-many mapping. That will give us a function, right? Now, guys, if we happen to do the following, if we recognize that we've got a many-to-one situation, many-to-one, then we said that in itself will not be a function. We'll call that a relation. Now, the next word that we want to introduce is this was a mapping going that way. One to many, one to one, and even many to one. Okay? What we're going to now ask ourselves is, what's this thing inverse? Inverse. Hey? The easiest way that I can talk about it is, if you remember right back in primary school or even in grade 8 and 9, they talked about an additive inverse. Talked about a multiplicative inverse. What does that mean? It's the thing that undoes addition. So the additive inverse of +2 would be -2. It undoes what you were doing. So remember we said a function is a rule that we follow when it takes the input and it makes the output. Now, the inverse is the rule that takes the output and gives you back your original input. So what do? We take from the output values and we try and get back. We do the reverse operation and we go in the opposite direction. That blue line represents the inverse operation. It's the inverse mapping. Now, can you see something? If the function is 1-to-1, then what we're going to say is the inverse will be 1-to-1. And that means that the inverse of this particular example will be a function. But what about this one? When it goes many-to-one, well, we know many-to-one in the forward direction is going to be not a function. This is going to be a relation in the reverse direction. So this is a relation because it's not giving me a unique. Many things are giving me one answer. But have a look at this. Quite interesting. A many-to-one, which we don't often talk about in grade 12 certainly, but the inverse of this function is actually, the inverse of this relation is actually going to be a function. How's that? That's quite amazing. So guys, I hope you've got that very clear. What is sometimes asked in the questions, though, can be confusing because there's terminology. I've talked about these things as being inputs. What they sometimes use is the terminology a domain, and the output is the set of numbers in the range. So we call this the x, that the y. When we're looking at the output, or the inverse at least, we take the x's and y's and we swap them around. That will give us an inverse. Now, let's start by looking at one example where we know it's a one-to-one relationship. So I've got a question that combines two things. It's got two types of functions. This one, f, is an exponential function. Okay, it's the line f of x equals 3x. And I'm just going to make a note here that this is one-to-one. So I'm expecting that the inverse of this function is going to be a function. But take a note at the second function here. It's x squared minus, g of x equals minus x squared. And there it's there. What do we notice here? It's one to many. So if we go the opposite way around, and the reason I said it's one to many, because 1 over here, sorry, it's many to 1, not 1 to many. I've written it incorrectly. So let me just correct myself there. It's many to 1. Many gives me 1. Gives me the same answer. So if I take that one particular thing, it will give me one unique answer. But that point over there will give me the same unique answer. So it's still a function. It obeys the vertical line test. But I hope you can see that if I go backwards and I go from 1 to many, I'm in trouble. If I do the reverse, 1 to many, then I'm going to be in trouble. And a many to 1 is not going to be an example of an inverse that is a function. We'll try and sort that out in a little while. So let's get into the question. It's question number 2. The first thing we're focusing on is the f of x. It says write down the equation of the inverse of f of x equals 3x in the form of f to the minus 1x. Okay? And we're writing it in that form. Right, what are we going to do? Let's write it first of all as y equals 3x. And therefore, that's the function, that's f. That's the mapping of f. It tells you for every input, x input, you'll get an output of y. So let's talk now about if we swap these around. F primed x. Okay, what are we going to do? I'm going to swap the positions of the x's and y's around. I'm going to say, let's say that x is equal to 3 to the y. You got me? I've just simply exchanged them. The swapping of x and y, I'm now saying, in other words, I don't want to start with my x's. I want to start with my values in the range. And I want to get back to my domain. That's why I'm doing it like that. I'm starting with my x's, but I don't like it written like this. I want to rearrange it so that it can be written in the form y equals something. So how am I going to do it? Well, to deal with inverses, the inverse of an exponential is the log. So we'll simply, by definition, say log of 3x is equal to y. And so there's my function. There's my inverse. I can simply write it in the form. Don't leave it like that. I can simply write it as f primed x is equal to log to the base 3 of x. And there's my answer. Okay, hope you've got that. Make sure you can do this swapping around of x's and y's. You got a question?
I have some questions and comments. First comment is from Sovo saying, Abram, tell the teacher that for me there are no questions because I can see more answers on his face when he faces the screen. So that's a great one. But I do have people that have questions. One is from Matsubane Mnini, therefore says, I think overall I can conclude that all one-to-one functions have inverses that functions and all one...
That are functions. That's correct. Absolutely. Well summarized. All one-to-one functions have inverses that are functions themselves. Okay, excellent.
And all one-to-many functions have inverses that are not functions.
Correct, they are relations. So think about the things that are one-to-one, exponential, hyperbola, and straight line, except for that x equals a value, okay? All of the others are one-to-one examples. What about the many to one? The quadratic. and we'll come to that in a second. Just wait a minute. We're going to find a way to represent a quadratic as the inverse of a quadratic as a function as well. Normally, the inverse of a quadratic will not be a function. You're absolutely right.
No,
Okay,
let's continue.
shall we continue?
Yes.
So, second part. It says, on a set of axes, draw, and this is the important bit, and hopefully this will help us. Draw the graph of the inverse of f of x equal 3x. And then write down the domain of the graph of f primed x. Okay, so the inverse function. So, guys, what I like to do when I'm given this task is the first thing I'm going to do is I'm going to put my set of axes. Don't make them terribly big. It's just asking for a sketch graph. And I'm going to put the arrows on. Don't forget the arrows. We still label the graph as x and y, so that's not a problem. We make that the y, make that the x. Now, the thing that I do in my head, and even if I've got to do it on a rough piece of paper, I want to draw in f of x. We've got f of x drawn up for us over here. We know that this is f of x, and I can actually see it over there, the yellow one. I've got it. I'm going to draw it in on my graph. I know it didn't ask me for this, but it just helps me in my thinking. Sometimes, you know, the science teachers don't get this math stuff so quickly. It's a bit abstract, but we can use it in science. This section, it's really important to develop your thinking. If you're doing maths and science, then there are lots of things in science that are functions and inverse functions. Relationships that go one way and go the other way. Let me not get distracted. So, we know that value because this is y equals 3 to the power of x. And this point here was 0 and 1. Now, we want the inverse of this. And we've already written the equation for the inverse. And the inverse looks really scary to me. It's f of x equals log x to the base 3. You know what? I don't often come across log x to the base 3. And I'm sure you don't either. You could put that into your calculator and start to plot some points. But there's an easier way. And I want to remind you of that easier way. What you've got to do is you've got to take the line. Remember what we did when we got the inverse. What we did is we switched the x's and y's. So what we're going to do is we're going to draw the line y equals x, and we're going to reflect the graph around the line y equals x. So if I reflect this point, 0, 1, then it's going to simply change. I want to change my color. So let me change my color to this blue line. It's not going to be 0, 1 anymore. It's going to be what? 1, 0. Got it? And notice now that this was going parallel to the x-axis. So I want my new graph to go parallel to the y-axis. I'm going to start it down at the bottom, and I'm going to grow it. So I've just flipped it over on its side. Fold it over. If I fold this point over, it's going to get down here. If I fold that point down, it's going to get somewhere over there. And that's exactly what I'm going to draw in. I'm going to draw that line in. Guys, you must know this. You must be able to do it. See the effect. This is f dashed x, or f primed x, and it's equal to the log to the base 3 of x. Label your graph so that people can see that you know what you're talking about. I hope you can see, just by the way, that the graph, using the vertical line test, where we use the vertical line test, is a function. So the inverse is a function. Even though it's getting closer and closer, it's asymptotic over here, it's still a function. Even over there, it's a function. So the function over here, the original function is a function, and the inverse of this function is a function. because they're both, the original one was 1 to 1. So the inverse is also 1 to 1. Hope you've got that. Okay, guys, next question. And it was the second part here. Write down the domain of the inverse. Oops, let's not go too far forward. Write down the domain of the inverse. Now, the domain of the inverse is very simple. What we're going to say is, what are the x values that are allowed? Notice that it's not going to cross over. It's never going to cross over this line. It's never going to cross over this line y equals x. We can't get values for the log function less than 0. So simply what we're going to say is that x has to be an element of bigger than 0 and all the way to infinity. And that's the domain. That's the domain of f of x. F dash x, not f of x. That's the domain of the inverse of f. Okay, guys, I'm going to have to hurry it up a bit because the next part of the question is exactly this. Why is the inverse graph of that line not a function? And then it carries on to the interesting question, which says, write down the possible restrictions of the domain of f dash x so that the inverse will now be a function. And hence, the last bit is draw the graph of the inverse functions. Okay, so first thing, if I take my quadratic, and I'm going to draw as quickly as I can so that you can see it, and I'm just sketching. Here was my graph. Just sketch very quickly, and remember what this line was. This was g of x, and it was equal to minus 2x squared, I think, minus x squared, that's all it was, minus x squared. Very nice and easy, and it's drawn like that. Turning point is 0 like that, and we're quite happy that this is a function. But guys, if we have to reflect it in the line y equals x, in this line here, then what we would recognize is we're going to flip it over. So this part will turn up onto the top, like that, and this part will turn down onto the bottom like that. And you can see quite clearly that if we look at it, what have we got? Abram, how many times does the vertical line cross through the blue line? Can you see? It crosses up over here.
Yes.
And it crosses up over there.
Times, yeah.
So it crosses more than once. Guys, it's not a function. Okay, so the inverse of this is not a function because it covers 2 points. How can we change that? I'm rushing on. There's another way we could do it. We could just change the x's and y's. So I could say y equals minus x squared, and then change them around and say, let me, in the inverse, make this x, make this minus y squared, and then solve, and you would find that you've got square roots coming in and all that. You've got positive and negatives, and so that's exactly where the problem is. We've got 2 values giving the same answer. You can do it that way. I'm not going to argue. I prefer to do it visually. How can we change it? And I've only got a minute left, but that's fine. If I say, let my function, my original function, change color. Let me get my original function. And let me take it as being this original function. And I say, let me only allow my values to be greater than 1. Then can you see that the reflected graph will be above the line? Or if I allow them to be less than 1, then they would be in the same way. So this one would follow if the function was allowed to do that. Okay, x less than or equal to 0, and this one, x greater than equal to 0. Abram, we've run out of time. Thank you for being with me tonight.
Thank you very much, John. I must say, you really rock. As the mindsetters say, you rock science, you rock maths too.
Thank you so much. Great to be with you, grade 12s. All the best, study hard, and I'll see you again soon.
Right, mindset is on that note. I just want to leave you with this greatest quote that says, mathematics may not teach us how to add love or how to minus hate, but it certainly gives us hope that whatever problem that you have, there's always a solution for it. So it's been a blessed evening sharing this time with you. We really appreciate from Team Mindset. Have a blessed evening. Cheers, guys. Bye.